All right. So first, we're gonna watch this little background. It's like we're gonna watch 3 or 4 minutes of it. Ignore the parts on gel electrophoresis because we obviously did not do gel electrophoresis, but we will later.
Hi, it's Mr. Anderson, and
Wrong
welcome
class.
to AP Biology Lab 6 walkthrough. This is on molecular biology. So it's the study of this material, deoxyribonucleic acid, that genetic material that makes life possible. In this lab, there are actually two parts to it. There's the transformation part, where we can transform a bacteria, make it different using a plasmid, and then gel electrophoresis, how we can separate DNA, how we can digest it, break it into fragments, and then separate it according to the length of those fragments. And so let's get started. The two things we'll do will be bacterial transformation. Transformation is when you're taking one bacteria, so let's draw an E. coli that looks like this, and here's another E. coli, and we're transforming this one by passing DNA between the two. In this case, we'll pass a little bit of DNA called a plasmid from one to another. The plasmid we'll be using is something called pGlo, so it's a way to actually get this bacteria to glow, fluorescent glow under a black light. Second thing we'll do is gel electrophoresis. Gel electrophoresis is separating DNA according to its fragment length. So we're basically running DNA through a gel. It's almost like Jello, and then we're separating according to the length of those fragments. So those are the two things that we're doing. The bacterial transformation we're doing is using a plasmid. This is the plasmid right here. It's called pGlo. Basically, pGlo is a section of DNA. So in a bacteria, they're going to have their regular DNA, but they're also going to have these little bits called plasmids. Plasmids give them ability to do something. So fertility plasmid would be an example, or resistant plasmid. So that's going to be one that gives bacteria antibiotic resistance. And so in this plasmid, it's been engineered. In other words, it's been built by humans. On one bit of the plasmid, we're going to have the origin of replication. That's where it's copied. These ones are also going to have ampicillin resistance. So when we grow them on ampicillin, only the ones that have picked up the plasmid are going to grow. Here we've got the glowing fluorescent protein. This is extracted from a jellyfish. And then I also have a trigger, arabinose sugar. So if you add arabinose sugar, they're going to make that glowing fluorescent protein. If there's no arabinose, then it's not going to show up. And so basically what we'll do is we'll have 4 different types of bacteria. The bacteria we're using is E. coli, Escherichia coli. So basically we're going to take some of the E. coli, and we're not going to give it the plasmid, so it gets no DNA. We'll plate some of that on what's called Loria broth. That's just basically food for bacteria. And then we'll plate some of it on Loria broth with ampicillin. So since it has an antibiotic, it's not going to be able to grow. We'll then add the plasmid to some of the bacteria. We'll grow some of them on Loria broth and ampicillin. Some will be able to grow, those that pick up the plasmid, and then we're also going to have some of those with this trigger, this arabinose sugar as well. And I'll show you what all those things are going to look like in just a second, but first let's discuss it. So basically what you get is a plasmid. A plasmid is a little bit of DNA. We're going to add it to bacteria, and so the protocol for doing that basically entails putting them on ice, the bacteria. You then add a transforming liquid. It's calcium chloride is what it is, and that causes them to kind of loosen up their membrane and more likely take in that plasmid. We're also going to heat shock them, so they'll be on ice, then we'll heat shock them, and then some of them will pick it up. And when I do this in class, you know, it's 2 or 3 groups out of 20 or 30 groups. We'll actually get it to transform. So there's a lot of chance to that. But if you get one bacteria to pick it up, you can get a colony of that, and then it's going to grow. And so basically, let's kind of talk through it. If bacteria doesn't pick up the DNA, what should it look like here? Well, we should have a lawn of bacteria. With ampicillin, we should have no growth here, because unless they get that ampicillin resistance, they're not going to be able to grow. LB ampicillin, the ones who get the plasmid, should be able to grow if they're transformed, and then these are going to be the only ones that actually glow. And so if we plate them on it, what we find is that the ones that actually didn't get the plasmid, but they're on Loria broth, what you'll get is they'll cover the whole of the plate. You can kind of see that on here. The ones who we try to grow on ampicillin, the ampicillin is going to kill them. In other words, it's going to kill all of them, since none of them picked it up. Likewise, on the ones who have the LB and the ampicillin, the ones that are transformed, we're going to see some colonies. So each of these colonies represent one bacteria that picked up the plasmid. It's able to make copies of itself and it's able to grow. So you can see not a ton of them were able to do that. But then finally we get the really cool plate where we've got LB ampicillin, so all these bacteria were transformed, but we also have that arabinose sugar, so they're able to use that to produce this glowing protein. And so you get this fluorescence in the bacteria. And so what do you need to understand? What a plasmid is, how it transformed bacteria, and then how that might be manifested in all the different growth on all the different plates.
All
Second
right.
one is called gel electrophoresis. Gel electrophoresis is going to use...
We didn't do gel electrophoresis, so you ain't got to worry about that. All right, so now I'm going to give you some notes on kind of the background of this. We're going to go over it, what should have been predicted to be seen, what should not, all that stuff. So, pGlo.
Are we writing pGlo?
You can write this down if you want notes going into this. You will be doing a claim evidence reasoning on Monday. No matter what your score was, you're going to be doing them in pairs on the whiteboards because you're going to be sharing them with each other and sharing them with me and sharing them with Dr. Siegel and all those folks. Yeah, they're coming in Monday. They may ask you questions like, what was this? Do you have pictures of this? Blah, blah, blah. Yep. And I'm going to tell them, find the kid who looks the most lost, ask them. Yep. Yep. Elysio's not coming Monday, apparently. Day ends in Y. Okay. Yep. All right. So, yeah. It's okay. Elisio knows I love him. It's all in good faith. So, let's say we've got this bad mamma jamma right here. Oh, our E. coli's got a break in it. This is my E. coli bacteria that we use for this. And if I look in E. coli bacteria, all bacteria, so we said in humans we've got linear DNA that's organized in rods called chromosomes. We've got 46 of them. If I look in bacteria, ooh, this is ugly.
It's beautiful.
Okay. Bacteria has circular DNA.
Oh, that's the DNA?
So, because DNA is double helix, it's supposed to be a double helix, but I never got good drawing genes, so haters, keep your comments to yourself. So here's that bacterial DNA. It's in a circular DNA, all right? Bacteria can also have another circular DNA right here called a plasmid. If this bacteria has this plasmid, it's going to give it certain traits. So this be plasmid. And this is the DNA. All right, so our goal is we want to insert one of these plasmids that has specific traits into the E. coli bacteria and thus transform it. Because if it gets that bacteria, it's going to behave different. And so that's our biggest goal is we need this E. coli bacteria to behave differently. And if I look at the plasmid that we're looking at, let's say I look at it and I go, ooh, there's my plasmid. We're going to have a couple genes on there. Gene number 1 that we're looking at, let's say, is right here. This gene is going to be for ampicillin resistance. So ampicillin, any clue what ampicillin is? It's an antibiotic, good. So ampicillin resistance. So this plasmid has this gene for antibiotic resistance. And it's also got, right here, a glowing factor. Ooh. Okay, this glowing factor. But this glowing factor, there's something special about this glowing factor. It must be activated. Can you what? Yeah, good luck. All right. And then finally, right here, this little part right here that we're looking on here, this is what's known as the glowing factor trigger. And so something's got to trigger this thing to activate that glowing factor. And the thing that triggers it Triggered by. So the thing that triggers it, my ex-girlfriend. No, arabinose sugar. Arabinose sugar. All right. I put OSE in all caps and I underlined it because if it ends in OSE, it signifies that it's going to be a sugar. So arabinose is a sugar. All right. So if the E. coli takes this plasmid up, it's resistant to ampicillin. Ampicillin's an antibiotic, meaning if I give it antibiotics, it's not going to die. And it could glow, but only in the presence of arabinose sugar. All right. So I'll let you draw that. I hope your drawings are beautiful. I hope your weekends are beautiful. And okay, Bonita, that's better than I could do. All right. And oh. Folks at home, people are writing this down. I hope you're enjoying this. Do what? Yep, this is our pGlo lab. We're going back and we're revising our claim evidence reasoning now. Because in the beginning we kind of just learned about the bacteria or the DNA structure and everything. Now we have a little bit more background, so now we're going to go back and revisit it. No, we're not doing the lab again. Can't afford it. That lab alone is like $500. No, total. It's like $150, huh? Expensive. Yep. Here at Series, we ball in. All right. So we talked about our goal here is to transform this. So we want to insert this plasmid that we have. This whole thing right here was our plasmid. All right. Our goal was to insert this into E. coli bacteria. If we insert this into E. coli bacteria, we could change the behavior of bacteria. And another word for change is transform. And that's what our biggest goal was. We want to make E. coli bacteria antibiotic resistance. And so we had to look at the whole setup for this whole lab. And if I look at it, we had a couple different plates. So plate number 1, let's say this is plate uno. It was LB. So this first plate was nothing but LB. And it had minus pGlo. All right. And the pGlo, so this, meaning this little plate right here did not get that pGlo plasmid. So if I looked at the E. coli in there, all it was is E. coli. No plasmid on there. And it's on a plate of something called just L'Oreal broth, meaning all it is bacterial food. So I took all this E. coli bacteria and I basically said, hey, here's hometown buffet. You're going to live here. So this one right here has no plasmid. No plasmid DNA. So I took this E. coli bacteria and put it on this plate that was just nothing but food for this bacteria. So what do you think our like a hypothesis would be? What do you think is going to happen here?
No transformation.
So no transformation would take place, but would bacteria grow?
Yeah, because it's eating off of the food.
It's eating off the food and there's no antibiotics on there. Okay, so we're going to have tons of bacterial growth. Okay, so hey.
Hi.
So we've got tons of bacterial growth because, so if we looked at this, there's no antibiotics to kill it. Not that I know of. Sorry. Good luck.
Okay.
Yep. So tons of bacterial growth, no antibiotics to kill it. So that's what's predicted that's going to happen here. Is you're just going to have tons and tons and tons and tons. Now we go to our next plate. Woo. No color. Had no soul. Okay. Our next plate right here. Whoa. If I look at this one is minus pGlo. Okay. And this was LB amp. So this plate right here is food and antibiotics. So there's no DNA, no plasmid, and it has antibiotics. So what would be our hypothesis? Okay.
It cancels each other out basically because there's no plasma.
Okay. Meaning, what'd you say, Juan? Okay. So there'd be no growth at all. So yes, it's got this big plate of food, but the other one says, hey, even though you got all this big plate of food, I'm going to kill you. Nice knowing you. All right. So no growth. Because the antibiotics kill the E. coli. No. Antibiotics kill the E. coli. But how come the gene doesn't save it? How come it's not antibiotic resistant? We didn't give it the pGlo plasmid. This one never even got it. So it can't be antibiotic resistant if we never gave it the pGlo plasmid. That's why that minus pGlo is very significant. Because right here, if I go to this plate and I go LB amp, and this one is plus pGlo. All right. If I look at this, it has the plasmid. And it has antibiotics. So what you think gonna happen? What? Why would there be growth? Okay, yes, the antibiotics are there, but now I also made it bulletproof because I gave it this gene. This E. coli bacteria, the ones that took up the plasmid, now aren't killed by ampicillin. So now we've made these bacteria that do not get killed by ampicillin because they took that plasmid up. So we're going to say E. coli that took up plasmid grow because resistant to ampicillin. But the real question, will it glow? It won't. It took up, okay, if I look at this plasmid up here, it got this plasmid, all right, and ampicillin resistance is on here, the glowing factor is on there, so it has the gene to glow, but why doesn't it glow? Because there's no arabinose sugar. So yes, I have this one here. It will not glow because no arabinose sugar. All right, and then finally we got our last one. We've got plus pGlo, and we've got LB amp era. Era signifies arabinose. So LB is the food, amp is ampicillin, era, LB amp era is arabinose sugar. So has plasmid, has yes, thank you, sorry, antibiotics, and has sugar. I'm going to put ARA for sugar. So hypothesis. what would happen? Okay, bacteria grows due to transformation. Okay, so bacteria will grow due to transformation, meaning that E. coli successfully took up that plasmid and started activating the genes on that plasmid. But will it glow? That's the real question. That's all a lot of you cared about. You're like, that's cool. I got bacteria. I got mold on my shower, so I can get that at home if I want to see it. Will it glow though?
Yes.
It will. Why? Sugar. So, will glow. So the sugar, arabinose, I'm probably misspelling that, activates trigger for the or the glow factor gene. So I'm just going to put GF gene. Cool story, bro. Now it's pretty sweet. You're going to sound like brilliant little niños. All right.
Yeah.
And so now we've got to kind of look at what's going to happen in your claim evidence reasoning. We've got all this right here. So we're going to make it. Sorry, did some of you still need that? Yes, I see people writing. Cam, you should start selling coffee out of here. You should start selling coffee out of here.
Not to Dad's though. That's Miss Janet.
Oh yeah, they do to the teachers every day. It's sweet. All right, so now we got to look at this. When we do a claim evidence reasoning, so let's say our claim. Our big claim that we're gonna make is E. coli bacteria successfully underwent transformation. Okay, E. coli bacteria successfully underwent transformation. And we could even add to that, and we could say underwent transformation and uptook, and took up plasmid DNA. Okay. For evidence, though, I'm not going to have you draw a picture this time. This time you're going to make a data table. On a claim evidence reasoning, you only want to include the evidence that's very, very that supports your claim. And our claim was E. coli bacteria successfully underwent transformation and took up the plasmid DNA. So we're not going to include all of our data that we collected. Let's say we looked at this and this was our data that we collected, we're not going to put all of this in our data table that we're about to make. Only the two that underwent transformation. So if I were to look at this, let's say I have red, we're not going to do this one. We are not going to do this one. But if I were to look at which ones we will do, we will put that in our data table and we will put that in our data table. Because those are the only two that support the claim that E. coli bacteria successfully underwent transformation and took up the plasmid DNA. So I'm then going to make a data table. Let's say my data table looks like... My data table is going to look something to the effect of this. This would be appearance. And this one's going to be LB amp plus pGlo. This is going to be LB amp era plus pGlo. Okay, and then we would write our appearances there. You don't have to draw it out. You're going to write, what did you see? We saw tons of growth. We saw no growth. We saw, or well, both of these, it should support it. So you're going to say we saw growth. This one we saw growth, but it was glowing. This one we saw growth, but it was not glowing. That's all you're going to write. You're not going to analyze why yet, because you're going to do that during the reasoning portion.
No.
Hurt. All right. We almost done. We almost done. Here's the guts of your thing. All right, so on this reasoning now, you're going to tell me, oh, on this one, LB-amp plus pGlo, we saw bacterial growth did take place, but wasn't a ton, and it didn't glow. LB-amp era, bacterial growth took place, wasn't a ton, it wasn't anywhere near as much as the other one, but this time it was glowing. So now I want to know how and why evidence supports the claim. This is where you're going to go into for example, the LB-amp plus pGlo. Our hypothesis is said, so you're going to have growth there, and you're going to talk about how the reason that there was growth in the LB-amp plus pGlo was that because the E. coli bacteria took up the plasmid. This plasmid was activated, making it resistant to the antibiotic ampicillin. However, it did not glow because there was no arabinose sugar that was present to activate that trigger for the glowing factor. And then you would go into the LB-amp era plus pGlo. Bacterial growth did take place here because transformation was successful and the E. coli bacteria took up the plasmid. This time, though, arabinose sugar was present, which activated the growth or the glowing factor trigger, which caused that gene for glowing to be activated due to that arabinose sugar. All right, and so that's what's going on in the reasoning. And then you need to do that, and then you need to briefly discuss briefly discuss the topic of transformation. Prokaryote DNA, plasmid, and I'm trying to think of anything else. Anything else I'm missing? Nope, those are good. And plasmid. This kind of shows that you know what you're talking about. So this is like, hey, here's what happened, here's why it happened, and then shows that you're an intelligent young adult. Well, most of you. Some of you have given up. Still love you.
Do we have to do antibiotics?
Oh yeah. We'll say plasmid and antibiotics. If you looked on a lot of your previous ones when you did it, you wrote out like, this one was glowing, this one was glowing, that was cool. And I said, why is this significant? You didn't explain anything else as to why was it significant that the pGlo one was glowing? Why is it significant that, or the LB-amp era was glowing? Why didn't the LB-amp one glow if that was plus pGlo? All right, so you've got to talk about all of that.